Hi, linear algebra students. So this is the third video on the projection makeup class. And in this video, we're going to see both the setup and an example on how to find the distance from a point P to a plane or a hyperplane, and to also find the closest point to P. Okay, so the closest point we will call x naught, but okay, so don't focus yet on the method or on this drawing, okay? I will explain that later. Focus on here because we're gonna engineer the distance between the plane and the point, okay? So first of all, what do we have in the problem? We have a point, we have a position vector of the plane as well as the normal vector, okay? So we have that. So in the first way, as what we did for a line, we will draw the vector q that goes from the vector p, the position vector, until you reach the point P. Okay, so this is step number one. You see, you compute the same vector. You go from the plane to the point. Okay, now the next step is to actually project this time around the vector q on the normal vector. So what will that give? Okay, so this will give you actually, let's erase the q here. I will put it here. Let's say okay, so I'm actually gonna put it like here. Okay, so this is the vector q. Now what is it gonna do? We're gonna find like the perp here, and we're gonna find, more importantly, the projection here. Okay, that being said, what's important to realize is that if we go along the perp, okay, so actually let's suppose that the perp is somehow like this. Well, we can draw the perp also here. So this vector here will also be the perp of q on n, and the projection will be here. Okay, so this guy right here will be the projection of q on n. And why does this give the shortest distance? Is because this projection is going to be perpendicular to the plane, right? So, okay, so we found this. Then the next step is obviously to compute the perpendicular component, because it will be important. What it will give where is the closest point. That will be your x naught, right? So once you compute both the projection and the perp, you find the distance by taking the norm of the projection, and the closest point is going to be p plus the perp. Okay. And before presenting the example again, I want to mention that this method works to also find the distance between two parallel planes. So I won't read. I drew this in order to not redo this. Okay, so this I wanted to do once in front of you, but I want to show you how it's the same context. Here it's a little bit more crowded because in reality, what you have is two position vectors. So your vector q will be one position vector minus the other. Okay, so that will be the vector q. Otherwise, it's the same trick. You project the vector q on the normal vector. The perp is going to be the same thing, and x naught will be this point over here. Okay, now x naught will be the closest point to P2, which is like the position vector of the second plane. But again, you can make sure that you're translating both of these points by the same amount in order to find other pair of closest points. All right, so let's have a look at an example with this method. Let's actually erase this and write the example over here. Okay, so we will be able to keep at the very least the method at the same time as we're solving the example. So we consider the point P which is 3, 5, 2, and the plane P, which will be x1 plus 2x2 plus 2x3 is equal to 6. And we're gonna ask the same questions as what we did before. So first, find the distance from P to the plane. And number 2, find the closest point. The closest point, okay, on the plane from the point P. Okay. So again, look, we're gonna answer these two questions at once, okay? So we're not gonna solve entirely one and then entirely two. We're gonna do them both at the same time because it follows this method right here. So the first step, okay, let's actually, let's start with the position vector here because we do have a point, like this is the point, but in this problem, the position vector is implicit. What do I mean by this? You can actually replace values of x1, x2, x3. That will make this equation work. So step number 1 actually, or I should call this step number 0, just to make this match with my method over here, is to actually engineer the position vector. So how do you do that? Well, you take the plane. Okay, so this is our plane. Okay, and what you do is you just replace values for which this works. Okay, so plus 2 times x3, which is equal to 6. So for example, one could decide to go for let's say 6, 0, 0, right? So what I mean by this is that you can choose your position vector to literally just be 6, 0, 0. Right? So you just find like x1, x2, x3 that work in this equation. Now that you have P, you can go ahead and calculate Q. So this is step number 1. So Q, which is equal to the point that we have now. So we can put it in vector form, 3, 5, 2. Okay. Minus the position vector that we engineered ourselves, which is 6, 0, 0. So what do we get here? We're getting negative 3, 5, and 2. And now let's erase, let's erase the drawing, okay? And I'll keep this as much as I can, but eventually I'll have to erase it as well. Let's now compute the projection. So projection of Q on the normal vector. Okay, well, the normal vector here, again, we have it, but it is implicit. Okay, so let's actually write it down. We have like this 1, then this 2, and this 2. So we know that the normal vector is actually 1, 2, 2. Okay, from that equation. Okay, so from there we can calculate the projection directly. So again, let's write the canvas. We have like plus and plus. Then we're going to have a sum of squares with the components of the normal vector. And then we multiply this by the normal vector itself. So let's go ahead. We have 1, 2, 2. Then we have 1, 2, 2. And we have here 1, 2, and 2. Now the vector Q is the vector we have right here. So we're going to multiply by negative 3, Then we have this 5 and this 2. So obviously the rest is copy grinding. All right, negative. So we have 10 plus 4, 14 minus 3, 11. So 11 goes on the top. Here we have 4 plus 4, 8 plus 1, 9. So 11 over 9 times the vector 1, 2, 2. And now obviously we're gonna put this 11 over 9 inside. So we're gonna have 11 over 9, 22 over 9, and 22 over 9. All right. Now, number 3, we calculate the perp. So now I need to erase the method, unfortunately, but we're basically just following it, right? So now that we have the projection, we can calculate the perp. So perp NQ. So it's going to be like the vector Q minus the projection. So the vector Q is this one right here. So we're going to have here negative 3, 5, 2. Okay. Minus the projection that we got over here. So 11 over 9, 22 over 9, and 22 over 9. So again, unfortunately, we're stuck being careful because we have like funky denominators. So we're having here 9 times 3 is 27. So negative 27 over 9. Here 15. Wait. 5 times 9 is 45. That's it. 45 over 9. And finally, we have here 18 over 9. Okay, so we just put that on the common denominator. And we subtract the vector, the projection vector that we have over here. So 11 over 9, 22 over 9, and 22 over 9. Now, what do we get out of this? So, negative 27 minus 11. So that's going to give us negative 38 over 9. So we're not very lucky. This is not reducible. 45 minus 22. So that will give us, I believe, 23 over 9. And finally, this one, we're going to get negative 4 over 9. So this is the perp. So step number 3 is done. Now, step number 4, okay, so the distance is simply the norm of the projection. Okay, so okay, so this is the I messed up my color code here. I wanted to put this in green. So yeah, I'll just like put that in green. So we have here, that's it. So 11 over 9, 22 over 9, and 22 over 9. Okay, so that this goes in green as well. As well as this. Okay, this should be in green, but let's not worry about it actually. I just want my projection vector to be the green vector, okay? Okay, so the distance is simply going to be the norm of the projection. So again, take the square root. And now you're going to square all the 3 components. So we're going to get here 11 over 9 squared plus 22 over 9 squared plus 22 over 9 squared. Okay, now this could get messy if you are not strategic. Okay, so notice that these are all factors of 11 over 9. So as you can see, you have advantages of leaving that 11 over 9 out. Okay, so let's actually, again, just write the color code. We have like 11 over 9 times the vector like 1, 2, 2. So one thing that you can notice is that this 11 over 9 is a common factor. So you can take it out of the square root. Don't forget the absolute value. And then what you will get is the norm of 1 squared plus 2 squared plus 2 squared. As you can see, much easier to compute. All right, so now the absolute value, we can safely drop it at this point. So this will give us 11 over 9. And then we have, here we have, what do we have? We have like 4 plus 4, 8 plus 1, 9. So that's going to be times 3. So overall, 11 over 3 is the distance. So that's going to be the answer for number 1. Now, I don't know if I'm going to have the space to do the number 5, but we are there. We need to find the closest point, so x naught. So what do we have? It's going to be the point P plus the perp. So the point P, which is 6, 0, 0, okay, plus the perp, which is here. Now this calculation, well, it seems more messy, but it's not really because, well, we have 2 zeros over here, so that works out fine. So then 23 over 9, and here negative 4 over 9. So what are we going to get? Well, 6 times 9 is going to be 54. Okay, so yeah, we're going to have here, so 54 over 9 minus 38 over 9. Okay, so let's not go too fast here, but we can safely say that we have 23 over 9 here. And now, unfortunately, I'm stuck erasing the sentence. Okay, so that will be enough. So we can pretty much safely say here that we have our negative 4 over 9 and our 23 over 9 right here. Now we just need to calculate the top component. So, okay, 58 minus 38 gives us 20, which means we're subtracting an extra 4. So it's going to be, here we go, 16 over 9, 23 over 9, and negative 4 over 9. So that is the answer to number 2. All right, before I close this video, there is a subsection that is optional to watch, but it is helping. So I just want to say here, check on supplements playlist. Okay. There is a series of 2 videos, distance from point to hyperplane. So what I'm doing in these 2 videos is I derive a formula for the distance, which is actually quite simple. And then once that formula is being derived, you can actually use it to in order to answer these types of questions much faster than what I did over here. So check the supplements. So it's not mandatory, though it's optional, because what's important is really that you understand this part. But I would recommend watching it. All right, hopefully this helps. See you in the next video. So, oh, by the way, this is it for the makeup class 5.5. Okay, so now we're moving on to 5.6, which deals with the cross product and the triple product.